Welcome to this explainer. Okay, so today we're tackling a really fascinating culinary engineering challenge. Look, we've all been there, right? You spend your whole Sunday meal prepping only to find out that your delicious creation has turned into this soggy, totally unappetizing mess by Tuesday. It's literally a universal problem. But today, we're gonna fix it. We are engineering a structurally sound taco casserole by mastering strict moisture control. We're approaching this not just as cooks, but, well, kind of like curious architects building a stable, delicious structure.
Here's our briefing for today. We're going to execute 5 critical phases. First, the moisture threat. Second, controlling lipids and evaporation. Third, assembling the structural matrix. Fourth, thermodynamic fusion. And finally, a red team counter-analysis. Let's dive right in.
Section 1, the moisture threat, the absolute enemy of the carbohydrate base.
To kick things off, we really need to define our objective. We are building what we call the taco casserole matrix. Basically, it's a high-protein, perfectly sliceable structure that's optimal for athletic recovery and for meal prep practitioners who actually need their food to hold up over several days. But here's the catch. The entire success of this matrix relies on one single thing: a stabilized carbohydrate base. If your base fails, well, the whole structure collapses like a house of cards.
So, the crucial question we have to ask ourselves is, how do we prevent a soggy carbohydrate base? I mean, how do we stop rendered fats and those watery, aqueous juices from dripping down and just chemically dissolving our carefully laid foundation into a sad, gummy paste? That is exactly the problem our protocols are designed to solve.
Moving right along to Section 2, controlling lipids and evaporation. We call these protocols alpha and beta. All right, we're now entering the active combat phase against our two primary enemies, liquid lipids and aqueous tomatoes. To execute Protocol Alpha, you have to control your inputs. You must use exactly 90% lean ground beef or ground turkey. Listen, this 10% fat maximum, it's a hard rule. If you use higher fat ratios like an 80-20 or, a 73-27 blend without aggressively draining it, you are literally asking for structural failure. Those rendered liquid fats are just going to pool at the bottom of your dish and dissolve the carbohydrate base. So we stop the problem before it even starts by controlling the fat. Once you've got your lean protein, you're going to take 1.5 pounds of that meat and get it into a large skillet over medium-high heat. You need to break the meat apart and execute the Maillard browning reaction. And hey, this isn't just about, cooking the meat. It's this incredible scientific process of developing complex flavor compounds over 5 to 7 minutes of direct heat.
Which brings us to Protocol Beta, the evaporation mandate. This is absolutely critical. Our source material stresses that putting wet taco meat directly onto starches will cause them to act like giant sponges, instantly turning them into gummy mush. So to prevent this, right after browning your meat, you toss in your spices: paprika, cumin, chili powder, along with a 14.5-ounce can of diced tomatoes, juices and all. Then, reduce the heat to medium and let it simmer uncovered. You're forcing the evaporation of 80 to 90% of that visible liquid. After about 7 minutes, your meat mixture should be super thick and actually hold its shape on a spoon.
Okay, Section 3, assembling the structural matrix, or Protocol Gamma.
Here is where the magic happens. We're constructing our architecture in a standard 9 by 13-inch baking dish. The very first decision, the base material. When you compare corn tortilla chips against flour tortillas, the engineering data is crystal clear. We use about 2 cups of slightly crushed corn tortilla chips because corn acts as a vastly superior structural foundation. Flour tortillas simply dissolve way too fast under the inevitable heat and residual moisture. Corn gives us that mechanical resistance we absolutely need. Now, to guarantee structural integrity, you must follow this exact sequence. Step 1, the base. Spread your crushed corn chips evenly across the bottom. Step 2, the buffer. Spread a thin, really even layer of refried beans directly over those chips to anchor the next layer. Step 3, the payload. Carefully scatter the reduced, low-moisture protein matrix that we just engineered on the stove right over the beans. And finally, Step 4, the lipid shield. Blanket the top entirely with 2 to 3 cups of shredded cheddar or Monterey Jack cheese. Remember, sequence is everything here. All right, on to Section 4, thermodynamic fusion and finishing, also known as Protocol Delta.
350. You are going to bake this assembled structure at exactly 350 degrees Fahrenheit, that's 175 degrees Celsius, for a precise 20 minutes, Precision in temperature is literally what separates a successful, solid matrix from a total collapsed failure.
So, why exactly 350 degrees? Well, because this specific temperature threshold induces a vital phase change. It melts that top layer of cheese into an impermeable hydrophobic barrier. It's a lipid shield that perfectly binds the whole casserole together. And at the exact same time, 350 degrees is low enough to prevent those foundational corn chips at the bottom from scorching. It really is a perfect thermodynamic balance.
Once it comes out of the oven, you must execute the cold finish. You absolutely have to let the structure rest for a mandatory 5 minutes so the matrix can properly set. Then, and strictly then, do you apply your aqueous cold ingredients. We're talking shredded lettuce, diced raw tomatoes, sour cream. You apply these only at the exact moment of serving. The goal here is to preserve an extreme thermal and textural contrast between that hot, fused matrix below and the crisp, cold elements right on top.
Finally, Section 5, Red Team Counter-Analysis. It's time to debrief the method and check our biases.
So, the devil's advocate actually presents a really compelling argument here. They state that regardless of how aggressively you evaporate the meat juices during Protocol Beta, sealing baked tortilla chips under a layer of hot meat and melted cheese will invariably result in some loss of mechanical crunch. They argue that the mathematically superior method is actually what they call a deconstructed casserole. Let's compare these two philosophies head-to-head. The matrix method, which we just built, provides sliceable convenience and incredible flavor fusion through baking. But the deconstructed method, it takes a totally different path. Culinary purists prefer baking only the meat, beans, and cheese matrix together in a dish. Then, when it's time to eat, they use fresh, room-temperature tortilla chips to scoop and dip into the hot matrix. This guarantees absolutely 100% crunch retention.
Furthermore, we need to run a quick bias check on our own matrix. Historical data confirms that this entire casserole format is a distinctly American mid-century convenience invention. It firmly belongs to the category of Tex-Mex cuisine.
In fact, our matrix bears no real resemblance to authentic Mexican taco preparation. Authentic methods actually align a lot closer with the deconstructed purists. In authentic prep, the corn tortilla is strictly isolated from prolonged moisture exposure prior to the exact moment of consumption. The base is protected until the very last second.
We've analyzed the moisture threats, we've executed the evaporation mandates, built the architecture, and reviewed the structural counter-arguments. So, armed with all this robust engineering data, the choice is ultimately yours. Will you carefully construct the fused, sliceable matrix for your meal prep, or will you join the purists and deploy the deconstructed method for maximum structural crunch? Whichever protocol you choose, you now have the blueprint. Thanks for joining me for this explainer, and I'll catch you next time.